Hi everyone, I'm Whit Roy. Today I've invited an electrical tutor and an apprentice to have a conversation as they go through topics from the EWRB Electrician Theory exam. I hope you enjoy this style of learning.
Okay, Sarah. Tonight, let's go through topic 25, alternators. We're shifting from motors to generators now, so it's sort of the opposite direction, energy-wise.
Yeah, okay. Motors use electricity to spin, and alternators make electricity from spinning.
Exactly. That's the key idea right at the start. An alternator converts mechanical energy into electrical energy, specifically AC.
So it's like the reverse of a motor.
That's a good way to remember it, yep. Now let's start with the basic construction, nice and slow. An alternator always needs three things: a magnetic field, a conductor, and relative motion between them.
Right. Magnetic field, conductor, and movement.
Good. In small machines, the magnetic field might come from permanent magnets, but in most real alternators, especially large ones, the magnetic field is produced by DC field windings on the rotor.
Oh, so it still uses DC inside, even though it makes AC.
Exactly right. That's a common exam point. The DC just creates the magnetic field. The AC is induced in the stator windings.
Okay, that makes sense.
Now, there are two main construction styles. First is rotating armature construction.
That's where the output windings spin.
Yes, the armature rotates, the magnetic field stays still, and the generated voltage is taken off using slip rings and brushes. This setup is usually used in smaller machines.
And the other one?
The more common one, especially in power stations, is rotating field construction. Here, the magnetic field rotates and the output windings stay fixed in the stator.
So the AC comes straight out of the stator.
Exactly. Much easier to handle high currents that way. Now, because we're dealing with three-phase systems, the stator has three sets of windings spaced 120 degrees apart.
That gives three voltages at different times.
Yep, three sine waves, each separated by 120. That's how we get smooth, balanced three-phase power.
Okay.
Now, let's talk about rotor types, because this often shows up in exams. There are two main rotor designs. First is salient pole rotor.
That's the one with the poles sticking out.
Exactly. Salient just means sticking out. These are used in slow-speed machines like hydro generators or wind turbines.
Because water turbines don't spin very fast.
Correct, so they need lots of pole pairs to get the right frequency. The second type is the cylindrical or non-salient rotor.
That's smooth, right?
Yes, smooth and very strong. These are used in high-speed machines like steam turbine alternators. Usually only 2 or 4 poles because the rotor has to survive very high speeds.
So rotor type depends on speed.
Exactly, speed and prime mover, which brings us nicely to prime movers.
That's what spins the alternator.
Correct. A prime mover supplies the mechanical energy. Common ones include water turbines, which are very common here in New Zealand, then steam turbines driven by coal, geothermal or industrial boilers. We also have gas turbines, mainly for peak load or emergency generation. Diesel engines are used for backup generators and remote sites. And finally, wind turbines, which may use gearboxes or direct drive systems.
So whatever spins it affects the speed.
Exactly, and speed directly affects frequency. Now let's talk about how AC is generated, especially three-phase AC. When the rotor spins, it creates a rotating magnetic field. That field cuts across the stator windings, inducing a voltage.
Because the magnetic flux is changing.
Exactly, Faraday's law in action. With 3 stator windings spaced 120 degrees apart, each winding reaches peak voltage at a different time.
So we get 3 AC voltages.
Correct, and that's why three-phase power is smoother and more efficient for transmission in motors. Now the last part, and this is very exam important, is the relationship between speed, poles, and frequency.
This is the formula bit.
Yep, but it's actually quite simple. The key formula is F equals N times P divided by 60, where F is frequency in hertz, N is speed in RPM, and P is the number of pairs of poles.
Pairs, not total poles.
Exactly. That's a common trap. We can rearrange it to find speed. N equals F times 60 divided by P. So for a 50 Hz system, a 2-pole alternator runs at 3000 RPM, a 4-pole runs at 1500 RPM, and a 6-pole runs at 1000 RPM.
So more poles means slower speed.
Exactly. Fewer poles means higher speed required. That relationship is critical when matching an alternator to its prime mover.
Okay, that actually feels clearer now.
Good. That's enough for tonight. Have a proper rest, maybe catch a bit of rugby, or just switch off.
Sounds good. Thanks, Mark.
No worries. We'll pick it up again next session.